next question is question number 8. This is magnetic field. This is the direction of the electron, so the current will be in the opposite direction. So the question is, state the magnitude and direction of the force due to the magnetic field. So F is equal to B QV sine theta. So definitely the angle between the electron and the magnetic field is 90, so sine 91, so B QV. And according to Fleming left-hand rule, we can determine the direction which is towards the side P to Q, because field in this direction, current in this direction, opposite direction of the electron. So according to Fleming left-hand rule, so this is the direction from left to right. And then the Hall's voltage is given BI over NTQ. T is not time, this is thickness. So state the two faces between which the VH, okay? So this is the face, right? So first one is EHSF. EHSF, this one. And the second is FGRQ, so this one. And the next is use letter to identify the distance T. Distance T. T is actually the thickness. So this is the thickness, P into E, this one. This is the thickness. Magnetic field in this direction, current in this direction, so this is the thickness T. Now the next question is, we have to show that number of the charge carrier per unit volume of the aluminium is 6 into 10 power 28. Look, the density is given, and density is equal to mass per unit volume. So this is the volume of one atom. So volume is equal to mass over density. So this is 27U divided by density in kg per meter cube. So that's why I multiply by 10 power 3. So this is the volume of the one atom. Now the number density is number of electrons per unit volume. So number is 1, volume is this. So this is actually the number of the charge carrier per unit volume. Next, we have to calculate the Hall's voltage, which is BI over NQT. B is given, I current is given, and this N we have calculated. And then this is the charge of the electron, and this is the thickness. Thickness is 0.0910 millimeters, so 10 power minus 3 for the meter. So the answer is 8.0 into 10 power minus 7. And the next question is question number 9. Question is, define what is meant by electric potential. So work done per unit positive charge to move it from infinity to a point in the electric field is called electric potential. And remember, for a positive charge, electric potential is positive. For the negative charge, it will be negative. It doesn't mean that's a vector. It's a scalar. Because the work is scalar, charge is scalar, so the electric potential is scalar. Next, initial kinetic energy in joule. Look, it's given in 4.8 mega electron volt. So 1 mega electron volt is 1.6 in 10 power minus 13. So 4.8 into this 1.6, so it is 7.7 into 10 power minus 13 joules. So it is converted into. Next, the distance d of closest approach of the alpha particle to the gold nucleus. Look, electric potential energy is 1 over 4 pi epsilon naught Q1 Q2 over D. Now Q1 is actually the charge of the gold, which is 79E, and Q2 is the charge of alpha, which is 2 times E. So electric potential energy we have calculated 1 over 4 pi epsilon naught value Q1 Q2 over D. So D answer will be this. So 4.7 into 10 power minus 14 meter. Look, E into E, so E becomes square, so 1.6 10 power minus 19 square. Use the answer to comment on the possible diameter of the gold nucleus. Definitely the distance between alpha and the gold nucleus is greater than the diameter. So the diameter must be smaller than this calculated value. Next, This is about the band theory, and the question is, use band theory to explain why the resistance of the intrinsic conductor material decreases as temperature increases. Look, when temperature of the semiconductor increases, electrons in the valence band gain energy and jump to the conduction band, mean higher energy level. Holes are created by the electrons in the valence band because the vacancy of the electron is called hole. So the valence band has positive charge. Number of the electron in the conduction band increases with temperature. So thus increase in the number density of the electron in the conduction band decreases the resistance. And the next part is, this is operational amplifier. Thermistor is connected here, and this is a graph between temperature resistance and thermistor temperature in degrees Celsius. Now the question is, determine the temperature at which the light emitting diode switches on or off, right? So we have to calculate actually the temperature at which it is converted into positive to negative, mean output voltage converts itself from positive to negative, mean output becomes zero. So when output becomes zero, then the difference of the input must be zero. So non-inverting, inverting both must be zero. So when non-inverting, inverting zero, the ratio of the resistors must remain same. So we can write here R1 over R2, mean R1 over R2 is equal to thermistor temperature over this, so R3 over R4. So substitute the values, you will get the resistance of the thermistor 2.2 kilo ohm, and from the graph we can check the temperature, which is approximately 14 degrees Celsius. Next question is, state and explain whether the thermistor is above or below the temperature calculated for the LED to emit light. Look, diode becomes conducting when V out is negative. So the inverting voltage must be greater than this. For the large value of this inverting input, resistance must be lower than the previous value, which can be achieved only when the temperature is greater than 14 degrees Celsius. So this is the question. Now question number 11. Is about state Faraday's law of electromagnetic induction. Simple, induced EMF is directly proportional or just proportional to the rate of change of magnetic flux linkage, and this coil is given. And question B is given 9.4 in 10 power minus 4i, and this is the current and time graph. So same graph will be for the B, same graph will be the phi, because voltage, current, B, phi all are in phase in a single coil. Okay. Now the question is, there is no EMF induced in the coil. Remember, EMF induced is directly proportional to, or you can say equal to, d phi over dt. So the points where the gradient is zero, this is T1, this is T3, T5, T6, so T1 and T3. And then induced EMF is maximum, so where gradient maximum, so T2, T4, T6, so T2 and T4. Next question is, we have to calculate the average EMF when the current in the solenoid is reversed from in the time of 6, mean two direction. First one side, then other side, because reverse. So N d phi over dt, N B A over t. So it must be 2 times, because 2 direction, forward and then backward. So 2 times B value, current is 5 is given, and then area pi r square. So this is area, this is a time. So this EMF induced voltage is 0.1 volt. So this is the question. And then the last question is question number 12. We have to write about the random decay. Decay process cannot be predicted in terms of number of the radioactive nuclei and in terms of the time. Okay. Decay constant, probability of decay of any nucleus per unit time to decay, right, is called decay constant. And the next, Question is number of the air molecules divided by number of the radon molecules. Look, for the radon, this volume has activity this much. So 1 meter cube of the radon will have activity 0.6 divided by 4.8 10 power, this 125. Now activity is equal to lambda n, so n will be activity over lambda. So 12.5 divided by this lambda decay constant, right? Multiply by 60 into 60 because we have to convert it in second. So it's 5.96 in 10 power lambda. And now we have to take the ratio of the number of the air, number of the radon. Look, we have calculated 2.52 into 10 power 25 divided by 5 point this. So 4.2 into 10 power 13. This 2.52 into 10 power 2, this air number is given. We have calculated this radon. So the answer is 4.2 into 10 power 7.